between between the quantum PC conjecture and quantum fault tolerance against adversarial noise. And then finally, I'll give a new proof of QMA hardness of the local Hamiltonian problem with this promise gap using our construction. So I assume most of you have seen the Kitaev Circuit-to-Hamiltonian mapping before, so I'll be brief in reviewing it. So this mapping is the central tool in quantum complexity theory. So the goal here is to start from a dynamics, which is a quantum computation, and then map it to the ground state of a local Hamiltonian, which is a static object. So the natural thing that Feynman and Kitaev came up with is this thing called the history state, which is a superposition of the partial computations of the circuit. And the key innovation is the introduction of this clock register that keeps track of the time step of the circuit. And Kitaev, in his celebrated work, shows that this history state is the unique ground state of this Feynman-Kitaev HFK Hamiltonian. And the idea is you have a term H in, which makes sure that the circuit is initialized to the all-zero state. The term propagation term H prop that applies the gate as the correct time step. And you have a term H clock, which enforces some encoding of the time in the clock register. Yeah. So if you apply this to QMA, you will add another term to check the output of the verifier circuit. So this has many applications in quantum complexity and related fields. In the next slide, I'll briefly mention and compare this with classical circuit-to-Hamiltonian mappings. So what Kitaev proved is that this FK Hamiltonian has soundness of 1 over t cubed. And what that means is that when you apply it to a QMA protocol, so where you have a verifier circuit, you get a witness and from the prover and measure the first qubit and accept if the measurement gives you an outcome of 1. So what the statement means is that if there exists a witness such that you accept, then the ground energy density of HFK is very close to 0. You can think of it as exponentially close to 0. Whereas in the no case of QMA, meaning for all witness you reject, then the ground energy density is lower bounded by 1 over t cubed. So this implies that determining the ground energy density of the local Hamiltonian problem is QMA hard. And this is the quantum analog of the classical Cook-Levin theorem. So in this in the work of Cook and Levin, what they did is a similar thing for classical. So they have a mapping from an NP protocol, basically a classical circuit, to a max unsat instance, which is a classical Hamiltonian. So one quite interesting question that I think is interesting is kind of inspired by this recent paper by Garibian, which reviews quantum analogs of NP. And there are many natural quantum analogs of NP beyond QMA. So one kind of open-ended question that I just raised here is that maybe there's more than one quantum analog of the Cook-Levin mapping. So maybe we should try to find such new mappings. So, yes, yeah.
What exactly is the ground state energy density?
Yeah. Oh, so the ground state. So so you consider a Hamiltonian a sum of local terms, and each term, let's say, is normalized to have norm at most 1.
Yeah.
and then you take the ground state of the Hamiltonian, and then you divide the ground state energy by the number of terms in Hamiltonian.
Okay. Sure.
Yeah. Yeah.
Yeah. So then you don't have to kind of assume that the Hamiltonian is normalized before.
Yeah, basically, density here means you normalize the Hamiltonian. Yeah, and yeah, yes. So another more hopefully more convincing motivation is the quantum PCB conjecture. So here, it seems that after more than 20 years of studying the Kitaev mapping, it seems that this mapping is insufficient to prove quantum PCP. So for example, this paper by Bosch and Croissant, what they show is that you can be creative with the Kitaev mapping. So for those of you who have seen the proof of Kitaev mapping, so the key step in the proof is to lower bound the spectral gap of the random walk corresponding to the clock register, and the random walk there is a walk on a line graph. And what this paper shows is that you can try to be very creative and come up with other configuration graphs, but the best thing you can do is 1 over t squared. So what this means is that so t is the number of gates. So because t is at least n, this means that the soundness of the FK Hamiltonian is always 1 over poly n. So I want to tell you about this trick, which so we have talked to a few people recently, and people seem to be surprised that despite this result by Bosch-Croissant, there's a very simple trick that you can use to improve this to any polynomial. So you can improve this to 1 over t alpha for any alpha. So it's very simple, and it's due to Li Chen. What you do is you take m copies of the HFK, and then you put a term HFK on each subsystem. And then you can see that the ground energy density is still 1 over t cubed. But now the number of terms in the Hamiltonian is m times t. So now if you take m to be very large, like t over 100, then this now is a very small polynomial. So to me, this means that in the polynomial soundness regime, the degree of the polynomial is a semantical thing. Yeah. So what the quantum PCB asks for is a constant soundness. So quantum PCB conjecture says it is QMA hard to determine the ground energy of local Hamiltonian to this precision. And this is a wide open problem. So the one motivation for our work is that maybe even a weaker version of this conjecture is still open. So this is what we call the polylog quantum PCB conjecture. So it is the conjecture says it is QMA hard to determine the ground energy density to 1 over polylog precision. And if necessary, can also consider polylog local Hamiltonian. And to the best of our knowledge, this is also open. So maybe we should try to attack this question first. So this leads to a motivation to find a new circuit-to-Hamiltonian mapping. In particular, the question is, can we improve the soundness to polynomial in the circuit depth instead of the size of the circuit? So it's a simple observation that we made in our work is that actually this would be useful. And the reason is because we can show that QMA verification can be done in log depth. So if you can have such a circuit-to-Hamiltonian mapping, then you would have a proof of the polylog quantum PCB conjecture. Yeah, so actually there are 2 proofs of this fact, the fact that QMA verification can be done in log depth. So the first proof is you can use the FK Hamiltonian itself. So you first start from a QMA circuit, you take the FK Hamiltonian of it. And now in the new QMA protocol, you expect the prover to send the ground state of this FK Hamiltonian. And what you need to show is that if HFK is sparse, then you can measure the energy of HFK in log depth. So the original HFK Hamiltonian is not sparse. So yeah, you need to do a little bit of work to make this work, but I'll skip this here. So here's the circuit. Oh, sorry. The circuit is, so you expect the witness to be the ground state, and you do a constant depth quantum circuit to measure the terms, and then you perform a log depth classical computation. So yeah, so it's even, this statement is even stronger in that the quantum circuit is only constant depth. So the classical analog of this is you can just first map any NP protocol to the 2D Hamiltonian, which is NP-hard, and then you measure the energy in log depth. Okay. Second proof is also it comes from this ideas from this paper by Bill Rogin, in which he showed the QIP completeness of distinguishing short quantum circuits. So it unsurprisingly also applies to QMA. So now in this proof, you need the proof. You expect the prover to send the history of computation as a product state, and then you use swap tests to check the consistency between the time steps. This is a circuit, and the key observation is the swap test can be done in log depth. Yeah. And so to compare this with the previous proof, for this proof, you don't need to use FK Hamiltonian, but the quantum circuit is inherently log depth because of the swap test. Okay, so now I have told you about a motivation for polylog for new circuit-to-Hamiltonian mapping and QMA in log depth. So yeah, I'll tell you about our construction. So we do not achieve this circuit-to-Hamiltonian with 1/poly D soundness, but we make some progress towards it. Just to make it clear. Yeah. So So I'll first start from by saying how you can get from a quantum circuit to a tensor network, and then I'll fill in the other two steps. So let's consider a 1-qubit circuit. U applied on 0. So you can implement this with gate teleportation. So let psi u be the EPR state where you act on the second qubit by the gate U. So phi u is basically a quantum software that encodes your gate. And then what you do is you can prepare the 0 state and the state phi u, and then you apply, and then you project the register A and B on the EPR state, and what you get is your desired computation on register C. You can express this in terms of tensor network. So here's the notation that I will use in this talk. So 1-qubit state can be represented by this triangle with one leg pointing out. EPR state is this with 2 legs. This is the EPR state projector, and this is the phi u state. So it's a bit, I think it's a bit non-standard, but I think,
Sorry, Quynh.
yeah.
Like U bar or U transpose?
Oh, yes. Yeah. So yeah, I think, so I think this is U. Yeah.
Of course. Yeah. You go up and then you go down.
Yeah. So I guess like looking at this, you see that it's you. It's yeah, it's just you. Yeah. So here's the expression of this equality in tensor network. You have 0 and you have phi u, and then you hit these two registers by this EPR projector called, I'll call it P. Yeah, and then you get what you had earlier. Now this can be generalized to an arbitrary quantum circuit. So let's consider this brickwork circuit for simplicity. And what you first do is you prepare all 0 states and a product of the encodings of the gates, and then you hit the right place with the projector P. And what you get is you get the output of the computation at the rightmost column, and everywhere else you get EPR state. So in summary, we just encoded a quantum circuit into a so-called PEPS. So a PEPS is basically a state where you start from a product state. Usually the constituting states are the EPR states, and then you apply a local projector onto like the virtual like legs. Yeah. Yeah. So far you may be wondering that what I just did looks like we're doing some post-selected quantum computation, and also I haven't told you what the Hamiltonian is. So to get the Hamiltonian, what we do is we make the tensor network injective. So the observation is that, so before applying the projectors V, we had a product state, and this state, and it is the unique ground state of this Hamiltonian. Now, if P were invertible, so the PEP state is of this form. If P were invertible, then P would have been the unique ground state of the so-called parent Hamiltonian. So what you do here is you put P inverse. Yeah, like you conjugate each term in this Hamiltonian by P inverse. So you can easily verify that if P were invertible, then this state is the unique ground state of this parent Hamiltonian. So this is the motivation for the so-called injective PEPS. So a PEPS is said to be delta injective if the local maps have singular values bounded from below by delta. So this PEPS is not injective because P is a rank 1 projector. So injective PEPS in many-body physics are believed to be more physical than general non-injective PEPS. And the reason is people believe that it can capture gapped ground states, and there exist efficient algorithms under some vector assumptions.
Quynh, I think you've muted
yourself. Yeah, sorry. Yeah, so now what we do is we make the tensor network injective by replacing P by an invertible map Q. Okay, then we have this injective PEP state, which is the unique ground state of the parent Hamiltonian. So what Q do we choose? So in this talk, we choose Q to be of this form. So this is a linear combination of the original EPR state projector and the other projectors onto the other EPR states. And the weights of these projectors are delta. Now this Q is invertible. So yeah, so far what we have done is we go from a quantum circuit to now an injective PEPS and get the parent Hamiltonian. And the reason we choose Q to be of this form is because we can now interpret the circuit as a noisy circuit. So what you do is you apply now this Q map onto these two legs, and what you get is like this. This is the original thing that we had, and now we have these extra terms. Yeah, and you have this the XYZ polys here are basically noise that happens before you apply the gate U, and they are weighted by delta. So this is nothing but the purified depolarizing channel.
Can you go back one slide? Sorry,
Yeah.
because Q is the one that flies the unitaries U, right? Or should no, it just checks
the connection thing.
Yeah. Oh,
Yeah.
Is there a reason it has to be Hilbert-Schmidt normalized?
Is there a reason for what?
Yeah,
Sorry?
why the sort of slightly funky normalization with the square roots and the square?
Yeah, so it doesn't have to be normalized like this, but I'm choosing it to be this way because then like the state yeah, I'm just normalizing the state like right now. So you can think of this as like at probability delta squared, you apply one of the three Pauli's errors, and with yeah. Yeah, so yeah. So this is like your errors, and this is like your environment. Yeah, like yeah.
You have to sum of square normalize the state.
Yeah.
Just one more question. When you say psi product state here, psi pro, it already contains, like it's sometimes a product of a two-body state because it already contains these unitary states, but they're just not glued together yet. Like it's not.
Not yet. Yeah. Yes. Yeah. Yeah. So so now you can generalize this to a general quantum circuit, and what you get is now the injective PEPs is a superposition over noisy executions of the quantum circuit. And the weight is weighted by the Pauli weights of the noise. Just to compare this with the Feynman-Kitaev history state. So there, what they have is the superposition over partial computations. Yeah. So now we can just use quantum fault tolerance because the local depolarizing noise is a special case of so-called local stochastic noise model study in fault tolerant quantum computation. So as a summary of the procedure, you go from a circuit to this fault tolerant version, you map this fault tolerant circuit into injective PEPs and get the parent Hamiltonian. Now I'll tell you a bit more about quantum fault tolerance and how it works how it would work in our construction. So the ingredients that we need for fault tolerance is a quantum error correcting code and fault tolerant method to transform the encoded information in the code. So the difference between our construction and basically everyone else in fault tolerance is that for practical purposes, almost everyone assumes classical computation is free and noiseless. Whereas here, everything has to go through the injective PEP. So even the classical computation is noisy. So interestingly, the original threshold theorem by Aharonov and Benor does not require measurements or classical operations. So everything can be done within the quantum circuit, and the depth and the space overheads are polylog in the size of the circuit. Yeah. So some other remarks on the noise and quantum fault tolerance. So in quantum fault tolerance, we need to be able to do mid-circuit initializations. And this we can also do in our construction. And in general, as you might have already guessed, there's no particular reason why we need to choose that particular map Q. In general, we can try to choose other maps, but as long as it's invertible. So that means we can basically engineer the noise. So for example, we choose the noise rate, varies the noise rate according like across the locations in the tensor network. And we can even choose delta to be 1 over poly n, making the circuit effectively noiseless. But it depends on applications. Yeah. So let me now give a first simple application of showing computational hardness of injective paths. So the task, the canonical task in tensor network and many-body physics is to compute the expectation value of local observables. And previous works have shown that exact calculation of this is Sharpe complete for non-injective paths. And it's shown in this work by Shook et al. So our construction combined with Aharonov-Benoit's threshold theorem implies that injective paths is BQP-hard to additive error and Sharpe complete to multiplicative error. And for technical reason, for this result we cannot do this result with local observables, and we needed a so-called tree tensor network observable. So I'll explain a little bit more now. So I'll show the harder proof first. So this uses the fact that computing the probability, output probability of a quantum circuit is to multiplicative error is Sharpe-hard. So what we can do is we take the Sharpe-hard circuit, encode it in a fault-tolerant circuit, and then run it through the injective paths. And in Aharonov-Benoit, the output is encoded in the concatenated repetition code, and the logical error rate is exponentially suppressed if the number of concatenation levels is log n. So what you would do to decode the output of the circuit is to perform a recursive majority vote. And this can be encoded in a tree tensor network operator. And so a tree tensor network is basically a PEPS defined on a tree graph. And the physical indices correspond to the physical qubits in your code block, and the virtual Hilbert space correspond to the concatenation levels. Yeah. So for the BQP hardness results, it's simpler because earlier we want the logical error rate to be exponentially small because we want to maintain, we want to do this for very high precision for Sharpe, but for BQP, constant additive precision is good enough. So that what you can do is you can use a noisy classical circuit to fault tolerantly decode this concatenated repetition code into a single physical qubit at the end. And then you can read out this physical qubit using just a local observable. Yeah. So that's our construction and a simple application. So this has nothing to do with the apparent Hamiltonian yet. So now we'll look at the properties of the apparent Hamiltonian. So to apply the construction to QMA, so recall that we have this parent Hamiltonian. And now in parallel to Feynman-Kitaev, we can associate this term as the H-in term, and this term as the propagation term. So for QMA, you don't want to initialize all the qubits to the zero state, because you want to leave some open register to receive the witness. So what you can do is just you can remove some terms in this H-in term. So then now the ground state is no longer unique. The ground state is now any state of this one. And this psi here is any state, which is the witness you would receive from the prover. For QMA, oh yeah, so this is the a figure showing an example of applying this construction to QMA. Yeah, so for QMA, you also need an output term to check the output qubit. For example, you can put it here on the first qubit in the output of the computation. And if you are using fault tolerance, you might also want to make sure that the witness is encoded in a quantum code. So what you can do is you can just add the code Hamiltonian into the H-in. Okay, so now let me tell you the properties of the Hamiltonian. So for that, we need to define these two notions. So a state is a alpha combinatorial state if it violates an alpha fraction of term. And a state is an epsilon energy state if it has energy density of epsilon. So these are like definitions of states with respect to the parent Hamiltonian. Now we need one more definition with respect to the quantum computation. So a kappa adversarially noisy computation is a noisy execution of the circuit W, in which at each layer, at most kappa fraction of the qubits are deviated by an adversary. So this is different from the stochastic noise model that people usually consider in fault tolerance, in that the locations of the qubits that are deviated can be chosen adversarially, whereas usually in fault tolerance, the locations of the faulty qubits are random. And the error here can also be time correlated across circuit layers, i.e. This can also be a non-Markovian errors. Okay, so as mentioned earlier, we can the hope is to consider QMA in this polylog depth regime. So we choose D to be polylog. We consider this regime here. So what we can show is that 1 over poly D combinatorial states encode an adversarially noisy computation. And delta to the D energy states also encode adversarially noisy computation. So then this means if the depth is constant, then states with constant energy density still encode some information about the circuit. And if D is polylog, then in order to make these to be less than 1, we need delta to be 1 over polylog. So I'll now compare one property of our construction with Cook-Levin and Feynman-Kitaev. So let me focus on the theorem 1 for combinatorial states. So I'm restating theorem 1 in the case when D is polylog. So theorem 1 can easily be shown to be true for Cook-Levin. And in fact, because in Cook-Levin, everything is classical. Combinatorial states are the same as energy states. However, the Feynman-Kitaev mapping cannot achieve this property. And the issue is with the clock register. And here's an example of a combinatorial state that has no information about the circuit. So let's consider this state where on the clock register, we have an invalid clock, invalid bit string. So as a reminder, in Feynman-Kitaev, the clock is encoded as a unary encoding. So this is not a valid unary encoding of time. Now, the observation is that this state satisfies all terms in H in an H prop, but it only violates 2 terms in H clock. So this is a very, so overall, this only violates 2 terms in the HFK, and yet it encodes no information about the quantum computation. So so as you already see, for theorem 2, we only have delta to the D in this energy states. So we believe that the same statement is true, and like same statement as theorem 1 is true for 1 over polylog energy states, but we don't know how to show it yet. So let's say if this is true, then what can we say? Then if there exists a quantum fault-tolerant scheme that can handle adversarial errors, such that the depth overhead is polynomial in D. So D is the depth of the noiseless circuit, and let's say, and we want to convert it into a fault-tolerant circuit with depth poly D, then this would imply that the polylog quantum PCP conjecture is true. And note that here we only need fault tolerance for QMA circuits, which might potentially be easier than doing so for BQP. And the intuitive reason is because we have a prover. So we might make the prover do more work for us. So you might wonder if this is true in classical. And the answer is yes. And this is first observed by this paper by Anna Gao and Mario Sachedi. And what they show is using Cook-Levin, you can also show that adversarial classical fault tolerance implies polylog PCP. So the next question you might ask is, does adversarial classical fault tolerance exist? So the answer is also yes. You can use the PCP theorem itself to construct such a scheme. Yeah. And there are other schemes without using PCP directly. But as far as I know, this scheme does not give polynomial depth overhead. So yeah. Okay. So that's the connections between this construction and polylog quantum PCP. So now finally, as you may ask, I guess we should try to prove QMA hardness first before doing that. So this is what we can prove right now using the theorem 2 that you saw earlier. So we can show QMA hardness of local Hamiltonian with n to the minus log n promise gap. So now we're back to the stochastic noise world. So there's no adversarial noise. So basically, essentially using the same proof as the proof of theorem 2, we can prove that the spectral gap of the parent Hamiltonian is delta to the D. And more generally, this spectral gap can be replaced by the product of delta, like along a computational path in the circuit. And I'm stating this more general statement because we will vary the injectivity parameter across the paths. So this is one freedom that I mentioned earlier that we can have with the construction. So this implies that if D is log n, then the spectral gap is inverse polynomial. And then you can quite simply shows that the spectral gap of H parent translates to the promised gap of the total QMA Hamiltonian. So for QMA Hamiltonian, you have an extra term H out. So what can we say from this? So recall that we start from a circuit and need to first encode it into a fault-tolerant circuit. So then in applying theorem 3 from the previous slide, the depth that appears in the spectral gap lower bound is the depth of the fault-tolerant circuit. While at the same time, we know that the depth of W can be assumed to be log n because of the QMA log depth QMA observation that I mentioned in the first few slides. So now what can we do with this? So we can choose delta to be 1 over poly n everywhere in the circuit, making the circuit effectively noiseless, and then just take the fault-tolerant circuit to be the bare circuit itself. And then with this, we obtain that the local Hamiltonian with this quasi-polynomial promise gap is QMA-hard. And another observation is that if we could construct a quantum fault-tolerant scheme for QMA with constant depth overhead, then this would imply a new proof of QMA completeness of local Hamiltonian with inverse polynomial promise gap. So how much do we know about this constant depth overhead quantum fault tolerance? So it turns out that you can do this if you neglect classical computation overhead using existing topological codes. For example, by this paper by Hector Bombin. This is also doable in classical fault tolerance by just using the original von Neumann scheme. So I think it's an interesting question by itself to construct a fully quantum fault tolerance with constant depth overhead, or to know whether or not it's possible. So what we try to do is we try to improve this promise gap. As so we did not achieve inverse polynomial gap, but we can improve it to n to the minus log n. And the way we did it is to exploit the properties of the log depth QMA circuit using swap test that I showed earlier. So for this, we need to use the second proof of log depth QMA because we're trying to reprove QMA hardness of local Hamiltonians. So we cannot use the Feynman-Kitaev construction. Like we cannot use the proof number 1 for log depth QMA. So you can exploit the properties of this circuit, and then we use a recent quantum codes with so-called local greedy decoder. In particular, we use this good family of codes called quantum tenor codes. And then from this, we can get a log depth fault-tolerant quantum circuit, except for a small log depth classical computation, which we don't know how to make fault-tolerant. So what we did is within those small classical computations, we set the injectivity parameter to 1 over poly n. So this makes this small classical computations effectively noiseless. And then we apply the general statement of the spectral gap theorem. And then we can get n to the minus log n promise gap. Yeah. So to summary, I started by motivating a new circuit-to-Hamiltonian mapping by the log-depth QMA observation and the polylog quantum PCB conjecture. I describe our construction, and this gives new computational hardness results for injective PEPs. And then we show that our construction exhibits some properties similar to Cook-Levin, whereas Feynman-Kitaev does not. And then I discussed the connection between adversarial quantum tolerance and polylog quantum TCP. And then I give a reproof of QMA hardness of local Hamiltonian with this promise gap. And then discuss a connection between QMA hardness and fully quantum fault tolerance with constant depth overhead. So for open questions, of course, the main question is prove a similar statement as in theorem 1 to energy states. Second question is, we don't know if even adversarial quantum fault tolerance is possible, and how does it look like? So another question is regarding this fully quantum fault tolerance with constant depth overhead, and and then other possible applications of our construction. Yeah, that's all. Thank you for listening.